All right. Hello, everyone. Today, we are going to be talking about this whole idea of centroids by using integration. Last time, we talked about these common shapes, common areas, and we were able to just look it up in a table. Well, what if we have a case where we have some kind of function, y is a function of x, kind of like what I have drawn down here, and I want to know the centroid of this shape. Well, I can see I have my from last time I derived these two equations up here for my y bar and my x bar. And what that would require is for us, because it's with the area, with respect to area, would require some kind of double integration or some, or as an option, what I'm going to choose to do is a single integration of a thin strip. So if I'm going to look at this single integration of the thin strip, because that's my preferred method, and what that would look like on this drawing is I'm going to draw like some kind of thin little strip here, and if I were to analyze that thin little strip, I could start by dimensioning that strip and say from the y-axis it is some distance over, some distance x over, right? And then its width we're going to define as dx. As far as its height, I'd map it on over, and I have a total height of this element of y. And this is my thin strip that I'm looking at. So that thin strip, of course, would have its own little centroid. And so for its own little centroid, we'd have our own y bar. Now I'm going to put a little EL, meaning it's the centroid of just the element. And then also I'm going to have an x bar of that element. And so if we just look at the element and look up at our equations we derived last time, then the x bar would be equal to the integral of my x bar of this element dA over the total area, and the y bar would be equal to the integral of my y bar. So the only thing I've really done here is replaced that x and y with x and y of the element. Let's take a look at that element in particular and define some of these things. The x bar for that element is essentially x, because the way we think about this is dx is approaching 0, right? I mean, when we do our integration, so that the x bar of the element is essentially just x. And the y bar of that element is essentially 1/2 y, meaning whatever height I'm at any particular point, that y bar of the element would be half that height. And the last thing that we can say is the dA, which is basically the area of that shape, would be equal to y dx. So that's just that dx times my y, or base times height, would give me the area of that shape. Now these three little, now I did that specifically for this problem, or it is particular to this problem. However, this will be the key to most of the problems that we are going to be working in this class. Let's talk about the general process for solving these problems. The first step is that you want to find out what this equation is. So find y in terms of x if needed. After you develop that equation of y as a function of x, your second step is going to be to find the total area of your shape that you're interested in finding the centroid for. So we know the area is the integral of dA, or we can say it's the integral from 0 to x of y dx. Basic integration, just the whole thing. After you find that y, just integrate it. The third step, skip along, give myself a little room, is you want to find the integral of this x bar element dA. Well, what I can say is the integral of this x bar element dA, based on what I just drew up here in this little blue cloud thing, is that x bar element is basically x. So this would be the integral of x, and then my dA I can see is y dx. So this would be x times y dx, and this would be from 0 to x. The fourth step is to do the same thing with the y direction. So we're going to have y bar the element dA, and the integral of the y bar of the element dA is the integral 0 to x. Now we have, what is y bar? We said y bar is basically 1/2 y. So we have 1/2 y, and then we have dA, and dA we already said is equal to y dx. So this is times y dx. Now I can bring out the 1/2 because it's a constant from 0 to x, and then y times y is y squared dx. So I end up with these two new equations in essence to find my x bar the element and y bar the element. That'll work most times unless you have some odd shape or you're doing it about the other axes. So the last step would be to solve for your centroids, your x bar and your y bar, and this is the easiest part because it's just algebra. So your x bar is whatever you found in step 3 divided by what you found in step 2, which is what? Area, and y bar, same idea. So let's look at an example. All right, so here's my example. What I'm given here is some kind of function. Now notice the function has these other variables in there, this little h and this k in here. I do have h as an axis and I have a as an axis or dimension in the different axile directions. What I'm looking to find is the centroid, my x bar and my y bar for the shape. And I'm going to continue to use this thin strip analogy. So from this, I can already see that I'm going to have those same equations still hold true, that the x bar, the element, is equal to x, y bar for my element is equal to 1/2 y, and my area of that element is equal to y dx. So we said the first step is to solve for an equation. What did we say? We said it was solve for y in terms of x. Well, it's kind of given, but we don't know what k is. So we're going to solve for this constant k. Now, if you have to do something like this, you're going to use a boundary condition, meaning you want to figure out, what do you know about this thing? And what we know is at x equals a, I know that my height y will be equal to 0. That's usually the way these boundary conditions work. So subbing that in the equation, I have 0 is equal to h times 1 minus k a cubed. And from that, I can solve for k, and I'll let you do the algebra with that, 1 over a cubed. All right, so there we have a k value. I actually have an equation for my y as a function of x, and I have h times 1 minus x cubed over a cubed. So the second step we said was to find the total area of our shape, and to find the area we said we can just integrate from z. So if I plug in what I have now for my area, I have from 0 to a of h times 1 minus x cubed over a cubed. And so the integration isn't too hard. I can pull that h out. Since I'm doing it in terms of x, I have 1 minus x to the 4th over 4a cubed. And this is all from 0 to a. From there I can just plug it in and I end up with h times a minus a to the 4th over 4a cubed. And you could do some canceling and you end up with 3/4 a h. And then the third step, we said let's find integral of this x bar of the element dA. And we can do that with some more of this substitution stuff, because we said that's equal to the integral from 0 to a of x bar of the element is just x, dA is equal to y dx. So this is following along almost exactly with what we did up here, where I'm saying from 0 to x, x, y dx. The only difference is I have an a in here because that's what we're given for a variable in the x direction for limit. From here, I'm just going to sub in what I have. So from 0 to a, I don't know x, so I leave it as x. For my y, I have h times 1 minus x cubed over a cubed dx. I can, what am I going to do here? I could bring out the h and bring in the x. So I'm going to have h times the integral from 0 to a, x minus x to the 4th over a cubed dx. From here, it's just the integration piece, so this is equal to h And I have x squared over 2 minus x to the 5th over 5a cubed from 0 to a. And then from there I can bring in the a, and I'm just going to jump ahead because I'm worried about time here, and I have 3/10 a squared h. So take a minute, put in that a, see if you can factor everything out and come up with this more refined answer of 3/10 a squared h. It's just the fourth step. We said we want to find the integral of y bar EL dA, and so doing our substitution, what I can say is, forgot my dA, what I can say, that's the integral from 0 to a. And then for this y, we are still, for this y bar, the element is 1/2 y. So I have 1/2 y times dA, and dA is y times dx. Or I can bring out the 1/2 from 0 to a, y squared dx. Now I'm just plugging in that a value, right? So what I end up with is this y value. Where's my y? There's my y is equal to h times 1 minus blah blah, all that business, right? So this is h squared times 1 minus x cubed over a cubed. That quantity also is squared. So because that whole business is squared, I am going to have to do a little FOIL. Let me bring out that h squared to make it a little easier. So I have h squared over 2 times the integral from 0 to a of, and then if I FOIL out that 1 minus x cubed over a cubed, I end up with 1 minus 2x cubed over a cubed plus x to the 6th over a to the 6th dx. Now I can finally get to my integration, bring out this constant, or bring down the constant. Integration, I have x minus x to the 4th over 2a cubed plus x to the 7th over 7a to the 6th. All this from 0 to a. So plug in your a and do a little simplification. You end up with 9/28 ah squared. So the last step in this process is to finally find the centroids of the entire shape, or because we know that we have an x bar is equal to the integral of our x bar element dA over a. So that gives me this 3/10 a squared h. That's from the first thing I found, or second thing I found, divided by the area, which was the first thing I found, is 3/4 ah. So 3/4 ah. Of course, this a goes away with that one. Both my h's go away, and I end up with 12 over 30a, which I can simplify to 2/5 times a. Same idea with the y bar. Y bar is the integral of the y bar of my element over the area. So we found y bar, the element, to be 9/28. Can't even draw a 9 this morning. 9/28 ah squared over the area 3/4 ah. So I have this 1h goes away here, h there, my a's go away, and I end up with 36 over 84h, or simplified to 3/7 h. So that's it in a nutshell as far as finding centroids by integration. More examples will make the process probably make a little more sense. Hope that was helpful. We'll talk to you later. Bye.